Gas hydrates can plug subsea pipelines. Chemical inhibitors are injected to prevent this. They disrupt hydrate crystal growth at the molecular level, ensuring safe and uninterrupted energy flow.
Welcome to this video on hydrate kinetics, mitigation, and additives, part of our flow assurance expert curriculum. Prepared by Dr. Fahed Qureshi, who is an expert in the area of gas hydrates, thermodynamic, and kinetic inhibitors. He has long years of experience in the area of hydrate inhibitor and promoter development and lab testing using rocking cells. We begin with Section 1, the kinetics of formation. Remember, while thermodynamics tells us if hydrate formation is possible, kinetics tells us when it will happen. Thermodynamics defines the boundaries where hydrates exist, but kinetics governs the actual rate of formation. Pipelines can often operate within the hydrate stability zone for extended periods due to this kinetic delay. Kinetic processes occur in three distinct stages: nucleation, where stable nuclei form; catastrophic growth, characterized by rapid crystal expansion; and finally, agglomeration, where crystals collide to form plugs. The driving force for nucleation is represented by this chemical potential difference, which depends heavily on the ratio of operating pressure to equilibrium pressure at a given temperature. In flow assurance, time is our most critical variable. Being able to manage the time it takes for hydrates to form is essential for system safety. We must also account for the memory effect. When hydrates are melted and then cooled, they reform significantly faster because the water structure retains remnants of the hydrate lattice. Induction time, or TIND, is highly stochastic and cannot be predicted deterministically. It requires statistical modeling, as factors like high shear and impurities significantly shorten this delay. Moving to Section 2, traditional mitigation. Here we discuss thermodynamic hydrate inhibitors, or THIs. This, like methanol and MED, work by competing for water molecules. Their hydroxyl groups form strong hydrogen bonds, disrupting the rigid hydrate cage formation and shifting the equilibrium curve. When choosing between methanol and MEG, consider their properties. Methanol is highly volatile, while MEG is safer to handle but requires significant topside infrastructure for regeneration. The volume of THI required is a major logistical challenge. The need to supply large percentages of water volume is why the industry is shifting toward low-dosage alternatives. Operational constraints include high capex for MEG regeneration units and high OPEX for methanol due to partitioning losses, where inhibitors are lost to gas or hydrocarbon phases. Finally, Section 3, Low-Dosage Inhibitors, or LDHIs. These manage flow assurance by manipulating kinetics rather than thermodynamics. There are two main classes: kinetic hydrate inhibitors, which delay crystal growth, and anti-agglomerants, which allow crystals to form but prevent them from sticking together into a plug. Let's look at the kinetic hydrate inhibitor, or KHI, mechanism. KHIs, such as PVP or PVCAP, use polymer chains to mimic the geometry of hydrate cages, blocking water and gas molecules from adding to the lattice. KHIs offer a safe window for operations by extending induction time from minutes to days. However, they have a strict subcooling limit. Once the driving force exceeds about 10 to 12 degrees Celsius, they stop working. Anti-agglomerants, or AAs, act as specialized emulsifiers. Their hydrophilic heads bind to the hydrate crystal, while their lipophilic tails extend into the oil phase, creating a barrier that keeps crystals from clumping together. This table compares the operating envelopes of KHIs and AAs. While KHIs are limited by subcooling, AAs provide virtually unlimited subcooling protection, though they require a continuous oil phase to function correctly. Now we move to Section IV, complex behaviors and anomalies. Sometimes, chemical additives do the exact opposite of what we expect. This is the promoter paradox. Under certain conditions of concentration, pressure, and chemistry, what should be an inhibitor can actually act as a powerful catalyst for hydrate formation. While promoters are useful in gas storage applications, they are dangerous in flow assurance. Even minor doses of corrosion or scale inhibitors can inadvertently accelerate hydrate plugging. Consider the case of citric acid. While models suggest it should inhibit hydrates, experimental data shows that under specific conditions, it actually promotes hydrate nucleation and growth. Concentration matters significantly. Many additives exhibit a dual nature, acting as promoters at low concentrations, while providing effective inhibition at much higher dosage levels. Unexpected promotion can occur through several mechanisms, such as reducing surface tension to aid gas dissolution, forming micelles that trap gas, or structuring water into prehydrate arrangements. Moving to Section V, we discuss validation and field strategy. How do we take these chemical insights and apply them to subsea operations? Because kinetics are unpredictable, physical testing is mandatory. We use high-pressure rocking cells to simulate pipeline conditions and establish the specific performance limits of our chosen inhibitors. Field strategies include continuous injection for stable operations, transient injection during shut-ins, or using synergistic chemical blends to maximize protection and efficiency. Although low-dosage hydrate inhibitors have a higher cost per gallon than traditional options like methanol, their much lower dosage rates lead to better long-term life cycle economics. That concludes our overview of hydrate kinetics and chemical additives. Thank you for watching, and we will continue with organic deposition in our next module. If you are interested in exploring these concepts further, I am open to consulting engagements, joint research, or professional technical training. You can reach me via the email addresses or LinkedIn profile listed here. Thank you for your time.